All right, let's dive right into this explainer and fundamentally shift how we think about building software with AI agents. If you've been working with AI coding tools, you know the immense promise, but you also definitely know the acute frustration of getting exactly what you asked for and then realizing it's completely wrong. Well, today we're going to fix that.
So why does your AI builder keep breaking code that already works? We've all been there, right? You ask for a super simple fix, and the AI helpfully hallucinates 5 brand new features, silently adds some unauthorized admin panel, or worse, regresses a bug you just fixed 3 weeks ago. It's so easy to get frustrated and just blame the model. But the hard truth? This happens because we're prompting the AI with wishes instead of binding specifications.
Section 1, the Spec First Revolution. Section 2, Prototyping for Decisions. Section 3, the Super Prompt Build. Section 4, Patching Existing Code. And finally, Section 5, the Executable Spec Wins. Think of today's explainer as medical triage for your codebase. We're going to hand you the exact tools you need for these specific, distinct phases of the software lifecycle. Let's get to it.
Section 1. The Spec First Revolution. We really have to debunk this persistent myth that an AI can just figure it out from a vague prompt. Our core thesis here is simple, but it's pretty radical. Correctness lives in the spec, not in the code itself. A snapshot of your codebase shows a builder what the code does, sure, but it never tells them which of those behaviors are actually load-bearing.
To put this into practice, we use a triage decision tree. You absolutely cannot use the same instrument for every situation. If it's a completely new thing with unsettled behavior, you use the prototype loop. If the behavior is totally settled and you're building fresh, that's the super prompt. But if you have an existing codebase and just need a targeted change, you use a patch prompt. Treating existing, living code like a fresh build is basically inviting a sprawling, unreviewable rewrite where the AI tries to reconcile everything all at once.
There's a massive difference between wishing and specifying. The ultimate anti-pattern is symptom-only, vague prompting. Telling an AI to make a secure search feature is literally just wishing. Spec-first engineering, on the other hand, provides executable constraints. Think along the lines of a role matrix mapping to explicit legal transitions, all backed by golden fixtures. Setting up these constraints sets the stage perfectly for our 3 specialized instruments.
Section 2. Prototyping for Decisions. Moving to Phase 1, where the idea is brand new, your primary goal is actually making decisions, not shipping code.
We call this the prototype loop. You're using a throwaway AI build specifically to settle a specification. Since you don't know all the rules yet, the AI is going to improvise to fill in the gaps. Those improvisations, those are the unsettled decisions you need to actually make. A prototype that runs beautifully on day 1 but teaches you nothing is a complete failure. Just remember the aphorism, ugly is fine, ugly is protective, because it completely stops you from falling in love with disposable code.
So here's how you work this metacognitive loop safely. You actually start by prompting vaguely, but you include a crucial decision visibility clause. You have to force the AI to list every single assumption it makes. Then, you probe the system with scenarios that stress the structure, make users disagree, test those boundary limits. When you step in and say, no, it should do this instead, record that immediately as a ratified decision in your spec format. Then feed that growing ledger forward into the next prompt. If you don't do this, those invisible choices just become your default spec through sheer inertia. Now, how do we get out of this loop? You graduate on evidence, not vibes. To avoid prototype promotion, where a messy demo quietly sneaks into production code, you need strict criteria. 0 provisional decisions remain. Your decision tables haven't changed for 2 sessions. Your golden fixtures can be confidently written as binding. Every unasked AI feature is fully dispositioned, and most importantly, absolutely no prototype code migrates to the real build. We only mine the decisions.
Section 3. The Super Prompt Build. Once that behavior is fully settled, we hit Phase 2. This is where we construct the super prompt to get it right on the very first pass.
The super prompt is your clean room build specification. It's a self-contained, heavily structured document that transfers exactly which behaviors are actually load-bearing. It hands the builder your invariants, your fixtures, and your test plans. A simple code snapshot just can't do that. A snapshot shows what the system looks like, not the actual physics governing it. This super prompt relies on an 11-part anatomy that constrains the AI from the top down. An AI builder reads top down, right? So we have to lock the system's identity, its scale ceiling, and its absolute invariance first. You must define the rules before you allow it to define the structure.
Let's spotlight a few of the most crucial, load-bearing parts of this anatomy. The core engine has to be explicitly I/O-free, so it can be tested completely offline. For the data model, you must separate identity fields from mutable fields, or the AI is going to guess wrong. Your golden fixtures need to be pasted inline, verbatim, and marked as binding. State machines must explicitly list illegal transitions, not just the happy path. And lastly, an out-of-scope section. You have to explicitly name temptations, because if you don't specifically say do not add fuzzy matching, the AI will helpfully build it anyway and totally ruin your system's strict logic.
Section 4. Patching existing code. This perfectly illustrates why Phase 3 is so incredibly delicate. When a codebase already exists and mostly works, the real danger isn't the builder doing too little. It's the builder doing way too much. Enter the patch prompt. This specifies a delta, not a whole system. It precisely dictates what must change, what absolutely must not change, and demands the failing test that actually proves the difference. It's a highly disciplined instrument that limits the AI to one single human-reviewable diff. It's literally your only defense against that dreaded, while you were in there, scope creep, where a simple bug fix somehow ends up refactoring 40 different files.
Look at the wild difference between these approaches. Saying, search seems broken, forces the builder to diagnose the issue, scope the fix, and write the code all in one massive, unreviewable pass. By delegating diagnosis to the AI, its random guess becomes your new spec by default. But with a patch prompt, you'll lay out the exact parameters. Observed output is 7, expected output is 3, scope is strictly limited to this specific query. It completely pins the AI to the ground. When you have a big feature to add, you don't send one massive prompt. You chain smaller patch prompts safely. Order them by dependency, not size. Always require a failing test first so the fix is mathematically provable. Put up a strict scope fence. Re-verify the chain so every new patch has to pass the test from the previous patches. And a brilliant little trick, harvest notice but didn't touch reports. This uses an honesty clause to queue up future work safely without allowing any unverified scope creep.
Section 5. The executable spec wins. This brings us to the golden rule of this explainer. When the code and the spec disagree, you escalate and litigate the spec. Never, ever quietly nudge whichever file just happens to be easier to edit.
I really want to share this powerful anecdote from the sources about propagated docstring drift. Basically, imagine a file where the actual executable test correctly expects the status of outdated, but 180 lines above, a human-readable docstring mistakenly says it should be contradicted. Because docstrings aren't tested in CI, they drift silently. Well, an AI mining the repo read that stale docstring, ignored the assertion, and propagated a massive bug into the new build. The executable line is checked constantly. Human prose is checked by nobody. The executable spec simply has to win.
I want to really hammer home this hard-hitting quote to anchor this whole concept in your memory. A super prompt without a verifier is a wish. An AI telling you I fixed it or I followed the instructions is just marketing. A failing test first demand, verified offline, is actual usable data. Never trust the self-report.
So, as you open up your terminal and fire up your AI builder today, I want to leave you with this provocative question. Are you building software or are you just writing wishes? Stop wishing. Start specifying. Thanks for joining me on this explainer, and I'll catch you in the next one.